In robotic reinforcement learning, we have witnessed robots mastering a plethora of skills, ranging from sports to challenging objects manipulation. Despite these successes, many roboticists and RL practitioners today still find the entry barriers intimidatingly high when it comes to integrating RL with real-world robotic systems. In this video, we're going to identify the causes of this very gap and address them with our work SERL, a software suite for simple efficient robotic reinforcement learning. Imagine a robot needs to learn to insert a small electrical component into a PCB board or route a flexible cable through a small clip. To initiate reinforcement learning in the real world, we can break it down into several key ingredients. We need an easy-to-use RL package with reliable implementation of the learning algorithm. We need to define the task with appropriate reward signals, a reset mechanism to perform episodic reset, a robot environment through which the policy interacts with the real world. Depending on the task, we also need a good controller that allows safe exploration of the environment without damaging the robot or the workpiece. SERL provides a framework that supports the above functionalities and enables seamless integrations with RL and robotic systems. In SERL, there are two major components: a high-quality implementation of the RL library written in JAX, and a robot environment tailored for RL. In SERL's RL library, we provide a flexible yet versatile implementation of the state-of-the-art Simple Efficient RL algorithm, RLPD, which supports learning from both online and prior data. We also include an arsenal of reward specification methods, including handcrafted rewards from ground truth state information, binary classifier rewards from positive and negative images, and vice reward classifier that learns a reward function during RL training. To speed up training in walk-like time, SERL also supports asynchronous training and inference, where the actor and the learner act in parallel. To better handle image observations, SERL provides ability to load and use visual encoders with ImageNet pre-trained weights. Aside from all the features provided, SERL is designed to be easily extendable for any new ideas from the users. As for the robot environment, SERL only assumes a GYM-compatible interface to interact with the robot. We provide working examples and environment wrappers for the Franca robot. Additionally, we open-sourced an impedance controller to enable RL training and contact-rich manipulation tasks on the Franca robot. The precise PCB insertion task demands fine-grained contact-rich manipulation with sub-millimeter precision. When trained on sparse reward signals based on end effector position, the agent learns to perform this challenging task with 100% success rate in 20 minutes. The cable routing task is representative of typical manufacturing and maintenance scenarios, where robots route cables or hoses. Lastly, we also experimented with a reset-free learning problem, where the task requires moving a free-floating object between two beings. The difficulties of reset-free learning becomes especially pronounced when manipulating such free-floating objects. Today, SERL starts as a software suite, empowering research in robotics RL. We invite you to explore this open-source framework, harness its capabilities, and push the boundaries of what's possible in robotic RL.